Welcome to The Explainer. Let's just dive right into this because we are witnessing an absolutely massive, rapid evolution in artificial intelligence. I mean, we've moved way beyond those simple text generators that just spit out answers on a screen. Today, we're dealing with autonomous AI agents. These are systems that can actually act out there in the real world, executing complex machine learning tasks, booking flights, or even writing code on our behalf. But as you can probably guess, with this incredible power comes a completely new and frankly kind of alarming security landscape.
Let me ask you a question. What if a hidden, completely invisible font on a totally normal-looking web page could secretly hijack your company's AI agent? It sounds like pure science fiction, right? But this is actually the shocking reality of web-based indirect prompt injections. Attackers are literally turning the web itself into a delivery mechanism for malicious instructions, effectively weaponizing the very autonomy we've just given to our machine learning systems.
So here's our roadmap for today's explainer. First, we'll look at the AI agent era. Then, the anatomy of AI attacks. After that, defending the AI system. And finally, we'll wrap up with regulation and compliance.
Let's kick things off with Section 1, the AI agent era, our new workforce.
To really grasp this security threat, we've got to make sure we're on the same page about what an LLM agent actually is. We're not just talking about a basic chatbot anymore. An LLM agent is an AI that integrates persistent memory, planning modules, and external tools. It perceives, it reasons, and it autonomously acts within complex environments. Think of these agents as cognitive controllers. They are actively making decisions and invoking external tools, like web browsers or secure internal databases, which, as you can imagine, completely shifts our whole security paradigm.
Because of this shift, our old security models, well, they're completely failing us. You see, traditional software is rigid. It's deterministic. It relies on the strict, hard-coded separation between passive data and executable code. But LLM agents, they operate on probabilistic, natural language reasoning. Inside an agent's brain, text, data, and executable commands all just sort of mix together in this open-ended environment.
And that brings us to the absolute core of this vulnerability. Instruction-data conflation. Because LLMs process literally everything through one unified natural language channel, they fundamentally struggle to tell the difference between information to be interpreted and commands to be executed. It's kind of like a security guard who can't tell the difference between their boss handing them an official work order and a random thief walking through the door wearing a name tag that just says, "Open the vault." To the AI, it's all just language.
Okay, moving on to Section 2, anatomy of AI attacks, or how attackers are exploiting the machine. So let's look at how a break-in actually happens. The flow for a web-based indirect prompt injection is shockingly simple but devastating. Step 1. The attacker embeds a hidden malicious prompt on a web page. They might hide it using XML or SVG encapsulation, meaning it's totally invisible to human eyes and standard web parsers. Step 2. An AI agent comes along and scrapes that seemingly benign page for some basic research. And Step 3. The LLM ingests that raw text, the hidden payload executes, and boom, the model's original instructions are completely hijacked.
Let's put this into perspective with a real-world scenario documented by OWASP. Imagine you tell your AI coding assistant, "Hey, run the test suite and email me the results." Sounds totally innocent, right? But if that test suite environment was compromised with an indirect prompt injection, the system could suddenly generate a subprocess call that exfiltrates your sensitive company data right back to the attacker. So a completely natural language request instantly turns into disastrous, unauthorized code execution. Crazy, right?
Now let's look at another major vector to see how this builds: retrieval augmented generation, or RAG, poisoning. Here's how it works. Step 1. An attacker publishes false documents online. Let's say a fake, highly generous refund policy. Step 2. A company's automated RAG system unknowingly indexes that poisoned content right into its trusted knowledge base. Step 3. A customer asks the company's AI chatbot for a refund, and the AI retrieves and confidently cites the attacker's fake policy as the absolute authoritative truth. Literally, the organization's very own knowledge base is weaponized against.
When we look at the emerging threat landscape, defined by the OWASP Top 10 for LLMs, sure, we have the usual suspects, like prompt injection and insecure output handling. But take a look at the newer vulnerabilities on this list. Things like excessive agency, where an AI is given way too much autonomy, or vector and embedding attacks that target those RAG systems we just talked about. These simply do not have a direct equivalent in traditional application security. We are dealing with an entirely new species of threats here.
And honestly, the threat just multiplies when these agents start working together.
In multi-agent collaboration attacks, researchers have identified what they brilliantly call the evil geniuses framework. Because agents in a network implicitly trust messages from their peers without verifying them, successfully jailbreaking just a single agent triggers a massive domino effect. The compromised agent passes malicious instructions to the next one, causing cascading alignment failures across the entire trusted network.
But perhaps the most terrifying vector of all are poisoned GGUF templates. Attackers are now actually hiding malicious instructions at the inference template layer, which is the very format used to run the model locally. Because this manipulation happens directly between the application and the actual model generation, it operates completely unseen by our current API security tools, meaning just one poison template could compromise millions of user interactions silently and at a massive scale.
All right, let's pivot to Section 3, Defending the AI System. How do we actually build our defenses?
The absolute foundation of AI defense relies on one very critical distinction. On one hand, you have training time alignment. This changes what the model knows, making the AI fundamentally less likely to generate something harmful. On the other hand, you have runtime guardrails. These change what the system is actually allowed to do. They sit right between the model and your infrastructure, making it much less able to act on misbehavior. You absolutely need both for a production AI system. Neither one is going to be sufficient on its own.
I really want you to absorb this quote from General Analysis. They say, runtime safety is not a feature you bolt on. It is an architectural property of the system. Let that sink in. You can't just build an autonomous agent and then slap a security filter on it at the very end like an afterthought. Security has to be fundamentally baked into exactly how the agent interacts with tools, its memory, and the outside world from day one.
So what does that secure architecture actually look like in practice? Well, it requires multi-layered defense strategies. First, you need architectural isolation, like using a dual LLM setup, where one model plans safely in complete isolation, while a totally separate, quarantined model interacts with the untrusted web data. Next, you need pseudonymization, basically masking sensitive data before it ever hits the generator. You're also going to need re-ranking to filter out any poison data in your RAG pipelines, and finally, robust runtime supervision, like a dedicated firewall, to constantly audit the AI's chain of thought in real time before it actually makes a move.
This brings us to our final section, Section 4, Regulation and Compliance. Let's talk about the law. The absolute game changer here is the EU AI Act, which is set to be fully active by the end of 2026. This is huge. It's the world's very first comprehensive legal framework for AI, and just like GDPR, it has a massive global reach. Even if your organization is based in the US or Asia, if your AI systems are used by or even impact EU residents, this law applies to you for sure.
The law takes a practical, risk-based approach divided into 4 tiers. Right at the top, we have unacceptable risk systems, like social scoring. Those are just banned outright. Next are high-risk systems, like AI used in critical infrastructure. Those face incredibly strict assessments and absolutely require human oversight. Then you have limited risk systems, like your standard customer service chatbots. For those, you just need clear transparency so users know they are actually talking to a machine. And finally, minimal risk systems are left to voluntary guidance.
Now, why does all this matter to your bottom line? Well, because the penalties for getting this wrong are severe. Organizations that fail to comply with the EU AI Act can face astronomical fines of up to 35 million euros or up to 7% of their total worldwide annual turnover, whichever is higher. Let that number sink in. Robust AI security is no longer just some technical IT issue. It is a literal existential business requirement.
All right, let's wrap up with our conclusion. Rethinking AI trust.
As we fully transition from passive text generators to highly capable autonomous agents, our entire concept of digital trust just has to evolve. So I want to leave you with this question. With attackers actively weaponizing the very autonomy that makes AI so powerful, how much unchecked agency is your organization giving its internal machine learning systems right now? It's definitely time to find out. Thanks for joining me on this explainer, and keep learning.